Okay, so for the second talk, we have 3 merged talks, actually. So they will all be given 10 minutes for the talk, and we will take questions at the end, so in 30 minutes. So the first talk is given by Chao, and this is on overlapping qubits.
Okay. Can everybody hear me? Okay. Thank you, Anthony. Good afternoon, everyone. It's my honor to be.
Leave the thing in your pocket. Turn it off. It should work.
Testing.
You have to put it.
Oh. How about this time? Okay. Thank you for joining us in this talk. This talk is a merge of 3 papers. All of them have been on the archive. I'm going to talk about the first one.
You have to put it up because speak up to put and speak up.
Hello? Okay. I'm going to talk about the first one, overlapping qubits. Okay.
Right.
Hello. This is joint work with Ben Ricard and Chris Sutherland from USC and Thomas Vidic from Caltech. So, oh, it should work.
What is this? You have to use on your laptop, I guess. I don't know where are your slides. What is it? Is it? Do you have plugged something in? I mean, this cannot work. You have nothing.
Oh,
put this in.
okay.
Try again. Maybe you need to find.
Okay. So before going into details of our results, let me start with some common motivation behind all the 3 papers. Okay, so nowadays quantum computers are beginning to scale up. They range from small machines for factoring to annealing optimization devices with more than 1,000 qubits. The heuristic reason that we want them to be able to scale is that a system with n qubits has dimension 2 to the n, which make them exponentially powerful. But here's comes the problem. Given such an enormously complicated system, how can we hope to understand it? And what kind of tests should be run to verify its behavior in an efficient manner? Turns out that the answer to this problem is not trivial. Small-scale quantum computers are relatively easy to test. You can simulate it on a classical computer, or you can perform state or process tomography. For large-scale quantum computers, the answer of the underlying algorithm are usually easy to verify, like in the case of Shor's factoring algorithm. But for quantum computer in the medium-sized zone, both tomography and simulation will become impractical. And also, the system is too small and too noisy to run algorithms with easily verified answer. So it seems that the most natural test would be quantum error correction. So today, we're going to only focus on scalable tests, which can verify different types of quantum resources. In general, a test consists of interactions between a verifier and one or more quantum devices. And based on the transcript, the verifier decides to whether accept or reject. And if we are given a quantum computer, it's natural to ask if it's really quantum or is it really just simulated by a classical computer. Of course, we also want to know how many qubits or how many entanglements do they possess. And if a given a cryptographic device, it will be necessary to test, to understand how it works, and in order to avoid numerous side-channel attacks. And in fact, device-independent cryptography is one of our primary motivation. So despite of purposes, what we want is a test for large that runs in polynomial time, which can apply to large-scale quantum systems. Also, it should output the right answer with high probability. It would be also nice to tolerate constant noise, because we really want to implement it in practice. So in my remaining time, I will explain a test for the dimensionality of a single quantum system. In some sense, it certifies how many qubits does a system have in an overlapping manner. And next, Andrea and Matthew will explain test for the number of EPR pairs shared between two separate quantum systems. They use the parallel repetition of non-local games like CHSH games and Magic Square games. So let me explain what means by overlapping qubits and how it applies to dimension test. Okay, so normally, an ideal quantum system is made of qubits in tensor product. In that case, operators on different qubits should commute with each other. But the problem is that in practice, due to noise, we can never have a perfect test which can certify this fact, even if it is so. So a more realistic assumption should be quantum qubits in a system can have a small pairwise overlap. So here we use the term overlap to quantify the extent to which operation on one qubit can affect the state on other qubits. So for example, if you have access to two qubits, meaning you can perform arbitrary unitaries on them, let's denote them by U1 and U2, and the overlap of these two qubits can be defined as the upper bound of the spectral norm of their pairwise commutator. So interesting consequence based on this definition we will show is that if we allow a pairwise overlap to be epsilon, the n qubits can be packed into a dimension, can be packed into a space with dimension only n to the 1 over epsilon square. So formally, we show that our first result is that basically the quantum system can cheat rather dramatically. In particular, n qubits can be packed into a polynomial n dimensions, which means provided that they can have slightly overlap. So that means if even before considering issues like noise, a system with n qubits can inherently lack any potential for exponential power. However, we also show that low-dimensional system cannot totally fool us. We give a test such that if a system with n qubits can pass this test with a probability, say 1 minus epsilon, then it must have dimension of at least 2 to the n times a factor of 1 minus n squared times epsilon. So before formulating our theorem, let me first define precisely what is a qubit and what does it mean by two qubit to overlap. So here we define a qubit in the space to be a pair of anti-commuting reflections. Reflections, as you heard in last talk, is a Hermitian with plus minus 1 eigenvalues, and we denote them by x and z. Here we are looking at the qubit from the Heisenberg picture because x and z are enough to generate all the unitaries and observables acting on this qubit. And indeed, starting from an anti-commuting pair, reflection pair, you can prove the isomorphism between the space and the space with tensor product structure. And under the same isomorphism, x is equivalent to a standard poly x, and z is equivalent to poly z, which is quite the standard definition of a qubit. And furthermore, if you have two qubits specified by their reflections x1, g1, x2, g2, and their overlap epsilon is defined as the maximum of spectral norm of the all their pairwise commutators. And in fact, it's easy to prove that if n qubits are in tensor product, if and only if their corresponding reflection pairs are simultaneously isomorphic to pairs of polymatrix, which precisely commute with each other. Okay, so here we give a proof sketch of our first results. We start by packing 3n nearly orthogonal vectors into log n dimensional space using the Johnson-Lindenstrauss lemma. And we group them into threes to obtain n nearly orthogonal subspaces. Then if we associate each vector with a matrix from the representation of Clifford algebra, then you can easily get n pairs of reflections having this simple form. Okay, the proof is very simple if you get the idea. It's just linear algebra. One thing to know is that our theorem only works for overlap at least square root of log n over n. Okay, so here is our dimension test. Suppose you have access to n qubits, and you first sequentially store n random qubits, each being either cat 0, cat 1, cat plus, or cat minus. And then you randomly choose the index, for example, j, and go back to measure again to see if the result is correct. And the point is, if n qubits are nearly independent, then if you measure j plus 1 to qubit n, then you will almost don't change the qubit j. So our theorem proves that if you can pass this test with a high probability, then this underlying system must have a dimension at least 2 to the n times a factor. And our test is pretty simple, but unfortunately it's sensitive to noise, which means you must have precise control of the poly x and the x and z operators. And so, in summary, our work defined a qubit to be an anti-commuting reflection pair, and our key conceptual contribution is that qubits can be arranged in a way that their corresponding observables only almost commute with each other. And based on this definition, we gave both positive and negative results. And an interesting open problem is to generalize our result to test for the functionality of a quantum system, not only its dimension. Also, it would be interesting to make our dimension test robust to noise and implement it in experiments. And last but not least, our dimension test is only a corollary of a stronger result, which has close connection with self-testing of EPR pairs, which is a topic of Andrea's talk. Okay, thank you.
So our second speaker is Andrea Coladangelo, and he will talk about by self-testing of EPR pairs via copies of tilted CHSH game.
Okay. So thanks, Rui, for the first part of the talk. I'll tell you about my work on parallel self-testing. It's not on? It's on? It's okay, I can talk like this. Okay. Right. I'll use that. Okay, sorry for that. So I'll tell you about my work on parallel self-testing of tilted EPR pairs using copies of CHSH. Let me just remind you what self-testing is, what we mean by self-testing. You've heard it from Anand, but so that we're all on the same page. So with device-independent self-testing, we refer to the scenario in which a classical verifier wishes to certify the state shared by two potentially untrusted parties. And this certification happens with just classical interaction and no other assumptions than the validity of quantum theory and that the two parties are not communicating. So as an example, we typically have in mind some non-local game or some Bell inequality whose maximal violation self-tests a target state in the sense that the maximal violation can be exclusively achieved when the two parties are making measurements on this target state. But more generally, I would like to say that a set of correlations, so conditional probability distributions PAB given XY of answers given questions, self-test a target state if they can be uniquely reproduced when the two parties make local measurements on the joint target state, up to some local isometry. So we'd rather say that it's a point or a locus of points in some quantum correlation set that self-tests the target state. So for instance, if we're thinking of self-testing via CHSH, we would consider the 2 to the n quantum correlation set. So this is all the correlations that can be produced by two parties that have two questions, and there's two possible outcomes for each measurement setting. When we're thinking of parallel self-tests using CHSH, we consider the 2 to the n quantum correlation set. Still two parties, but 2 to the n possible measurement settings, and 2 to the n outcomes for each setting. Okay, so let me get some notation straight. So for CHSH, we have Alice and Bob, and they get questions XY in 0, 1, and they answer with AB in 0, 1 respectively, and they win if A plus B equals XY. This is the maximal violation of CHSH that we're all familiar with. Several years ago, Popescu and Rohrlich, they proved that CHSH self-tests an EPR pair. And more recently, Rijkaard, Unger, and Vazirani showed that CHSH is rigid in the sense that a strategy that achieves a close to optimal maximal violation has to be close to the ideal strategy in some sense. Okay, so this was CHSH. Now I also need to introduce tilted CHSH. We will need this. So the tilted CHSH inequality is similar to CHSH, except that it has this extra alpha A0 term, which gives an extra alpha on the right-hand side. The maximal quantum violation, it's square root of 8 plus alpha squared. And it turns out that the maximal quantum violation self-tests what we will refer to as a tilted EPR pair, psi theta, cos theta 0, 0 plus sin theta 1, 1, where theta and alpha are related by this equation. And moreover, this self-testing result is robust in the sense that an epsilon close to maximal violation means that psi has to be order square root of epsilon close to the tilted EPR pair, up to a local isometry. Okay, so we have this self-test for a single EPR pair or a tilted EPR pair. And we wonder whether we can test many EPR pairs using copies of this simple inequalities game, so CHSH, tilted CHSH. So in the parallel self-testing scenario, Alice and Bob, they get questions x and y in 0, 1 to the n, and they answer with AB that are now in 0, 1 to the n. And we can think of the ith bits, so xi, yi, ai, and bi, as the ith set of question and answers, so for the ith copy of the game. Okay, so now I can tell you in words what my results are. So we show that correlations in the 2 to the n quantum correlation set, such that each of the n sets of question and answers is close to violating CHSH maximally, self-test n EPR pairs. And we generalize this to the tilted case. So correlations such that each of the n sets of question and answers is close to violating some tilted CHSH inequality maximally, self-test n tilted EPR pairs. And we also have a result on the magic square game, and there are correlations that are winning in each copy of the game, self-test 2n EPR pairs. 2n because each magic square game requires 2 EPR pairs to be played optimally. So I'll focus on CHSH and tilted CHSH, and then Matt will tell you more about the magic square game. Okay, so before this we had various self-tests, but just for 1 or 2 EPR pairs. the main work in parallel self-testing was McCaig's self-testing in parallel. And there he shows for the first time that you can self-test many EPR pairs in parallel. What we set out to do here is we try to show that using copies, that you can self-test many EPR pairs using copies of simple, well-known games, like CHSH and the Magic Square game. Okay, so now I'll give you a little more detail about the setup so that I can give you more precise statements. Okay, so in the parallel self-testing using copies of CHSH, as I said, we have questions xy and answers ab in 0, 1 to the n. We can define projections pi ax on Alice's side, and this corresponds to her obtaining outcome A on question X. And similarly, we define pi by on Bob's side. Now, in order to talk about the expectation value of the ith copy of the CHSH game, we need to define a few other observables. We let vi prime be the observable on Alice's side that gives her the ith bit of her answer when her ith question is xi equals 0. And we assume that the questions on the remaining n-1 copies are uniformly distributed. So this is the equation for vi prime, in case it helps you. And we define wi prime similarly, except that we're fixing the ith question xi to be equal to 1. Okay, so we can define v prime and w prime similarly on Bob's side, except that we have the subscripts running from n+1 to 2n to distinguish. And now, with a little thought, you'll agree with me that the condition that each set of question and answers violates CHSH maximally can be stated like this. Let me pull this up on its own. So this is our self-testing hypothesis. Each set of question and answers violates CHSH maximally. And our first result is that, oh, sorry. Okay, so at the end of the day, we want also the result to be robust. And so we wish to have an approximate self-testing hypothesis, which is that each set of question and answers is epsilon close to violating CHSH maximally. And then our first result is that suppose this approximate self-testing hypothesis holds, then psi has to be order n to the 3/2 square root of epsilon close to a tensor product of n EPR pairs up to a localized geometry. And we generalize this to the tilted case. Very naturally, the self-testing hypothesis becomes that each set of question and answers is epsilon close to violating some tilted CHSH for some angles theta I, and the theta i's for I equals 1 to n, they can be different. And then finally, we can state our main result, which is that suppose this self-testing hypothesis holds, then psi has to be order n squared square root of epsilon close to a tensor product of tilted EPR pairs with the corresponding angles, theta I, up to a localized geometry. So unfortunately, I don't have much time to give you details about how this is proved, but essentially, we leverage the CHSH rigidity of the equations in the self-testing hypothesis to produce sets of reflections that satisfy certain anti-commutation relations and commutation relations from a theorem of a work from the same authors of overlapping qubits. Yes. Okay, so I'll make one concluding remark, which is about the initial motivation for this work, which was slightly different. At the time I was thinking of another question, so the question of whether one can self-test all pure bipartite entangled states. So not just pairs of partially entangled qubits, but also pairs of partially entangled qubits for any D. So meaning for each such state, can we write down self-testing correlations? And the reason why I looked at testing many tilted EPR pairs is the following. That there's a natural isomorphism, of course, between states of n pairs of qubits and states of a single pair of qubits for d equals 2 to the n. What this means is that if we're able to self-test a state that is a product of tilted EPR pairs, then we can also self-test some state of a single pair of qubits for d equals 2 to the n. Of course, all of the states that are product of tilted EPR pairs, they do not cover all of the single pairs of qubits because we only have n degrees of freedom, one for each angle theta I. But nonetheless, as a corollary of our result, we deduce that we can self-test an n-dimensional subfamily of all the states, entangled states of two qubits. In the end, this question was recently solved in a joint work with Coudron and Valerio Scarani, where we actually use a very different approach, and we show that all pure bipartite entangled states can be self-tested. So on this note, I'll pass on to Matt, and thank you for your attention.
And our third speaker will be Matthew Coudron, who will talk about magic square games.
All right. Can you hear me? Everyone? Good? All right. And let me make sure I know how this works. That's backwards, probably. All right, there we go. Yeah, all right. So, hi, everyone. And this is the third of this QIP talk. One of the things, so this is a merged talk, and we realized at the beginning of this talk that, well, Ray at the beginning of this talk told you about results, lower bounds for how well you can pack partially overlapping qubits into a Hilbert space. We realized while we were all jointly preparing this presentation, that we're also establishing lower bounds for how well you can pack partially overlapping papers into a QIP talk. Right. So with no further ado, this portion of the talk, this talk about self-testing and rigidity results, is about the rigidity of the parallel repeated magic square game. And while all of these papers share some techniques, our particular angle on this problem, or the part that motivated us, was, by the way, that joke, I should give credit for that joke to Anand, who is my co-author here. You saw him talk earlier. Right, so our particular angle on this problem is that we really cared about the classical verifier component. So I have a picture here, and these self-testing type results, or the rigidity type results, usually have this kind of setting where you have two black boxes. We usually call them Alice and Bob, and they're untrusted provers, and you want to test them for some behavior. And what we cared about was that you're doing this as a classical verifier. So it's you yourself as a human being are a referee, and you can't look at quantum states, and you can't pass quantum states. All you can do is pass classical messages and receive classical messages from the boxes. So that's the setting for this work. All right. So since we're discussing the parallel repeated magic square game, I should first, backwards again. I think it's just upside down. There. I should first tell you what the magic square game is. I think in this audience, many people already know, but for those who don't know, the magic square game is the individual non-local game, and we're later going to analyze a parallel repeated version of this. But in the magic square game, just like it's the usual setting, you have two black boxes, or two provers, Alice and Bob, and you have a classical referee. And the classical referee passes at the beginning of the game. Alice and Bob imagine this 3x3 square in their head, and the referee passes them questions. And the questions will be, for Alice, he'll tell Alice a row, and for Bob, he'll tell Alice a column. And their job to report as answers, classical string answers, is for Alice to report 3 ones or negative ones that fill in the row, and Bob's job is to report 3 ones or negative ones that fill in the column. And the constraints on these answers is that the product of Alice's answers always have to be negative, and the product of Bob's answers always have to be positive. And the referee will also check that the intersection box, there's always an intersection box between every row and column, that they agree on that intersection. Okay, so that's the magic square game. If you cover this in a course or in reading or something, there's a simple argument for why you cannot win this perfectly with a classical strategy. But you can win it perfectly with an entangled strategy. And the entangled strategy looks like this. So Alice and Bob, the two black boxes, share a pair of EPR pairs. And they have this box full of observables. And every time the referee tells them a particular row or column, they report their answers for each box in that row or column by measuring the observable in that box. And so you can verify that the product of Alice's observables across every row is always negative identity. The product of Bob's observables is always positive identity. So that means the product of their answers will be -1 or 1. And their observable is the same. Since they have, for shared boxes, their observable is the same observable. So since they're sharing EPR pairs, that means they'll report the same answer. Okay, so this is the ideal strategy for the magic square game. Now that I've said that, I can state our main result. So the main result is showing that the in-round parallel repeated magic square game is rigid. And what do I mean by rigid? I mean that if the two black boxes are playing with some strategy which allows them to win with probability 1 minus epsilon, recall that the perfect strategy lets you win with probability 1, but that's hard for the verifier to test. But he can test that they're winning 1 minus epsilon of the time. If that's the case, then we can show that the player's shared state in this strategy must be close to 2 in EPR pairs. So it must be close to the n-wise product of the state shared for the ideal strategy. And it has to be close, its distance in the appropriate distance measure has to be polynomial in n and epsilon. So that was important to us. And the other thing that we can show is that the actual measurements when acting on the state have to be close to the ideal measurements. So they have to be close to the n-wise product of Pauli measurements. Right. So that's the main theorem, and it was important to us to do this using a test that has a classical verifier. And now that I've done the main theorem, maybe I can elaborate a little bit more on why that was important to us. So the reason the classical verifier is important to us is that, or rigidity results in general are important to us, is that they have applications in a lot of other results in quantum information. So that they sometimes can be used in device-independent protocols. They're also used in interactive proofs for the local Hamiltonian problem. And they're also used in delegation of quantum computation with a classical verifier. So anytime you have a classical verifier and you need to verify behavior of quantum devices, you're usually going to start out by using a rigidity result. That means that the scaling of parameters in your rigidity result is a limiting factor for the efficiency of the rest of your result. So that's some motivation for why you would want to improve rigidity results. Okay, and so that's the motivation, and I'll also say a little bit about the background. One of the really nice sort of pieces of progress on this topic, especially the testing of large games or the self-testing of large number of EPR pairs, came in a paper of McCaig called Self-Testing in Parallel. That was in 2015. And in that paper, he not only gives a self-test of n EPR pairs that has polynomial error dependence, but he also gives a test that actually has a classical verifier in it and tests in qubit Pauli measurements. But the portion that has a classical verifier in it has exponential error dependence. And so our goal, in some sense, our goal in this project was the improvement of that to polynomial error dependence while keeping the classical verifier along. Because he already has a result on polynomial error dependence. Okay. And the reason we wanted that was from the sort of all the same motivation that I just described on the previous slide. And there is some conceptual difference in the polynomial error regime when you're talking about a classical verifier. And I'll try to say a little bit about intuition for that. But basically, the idea is that if you have a classical verifier who's testing these boxes, and they're allowed to assume exponentially small error dependence, well, there's an exponential number of questions. So he's giving n questions for the parallel repeated, n times parallel repeated magic square game, right? So his question string is like n bits, or 3 n bits long. So they're an exponential number of questions that he can ask. But if you have exponentially small error dependence, you can union bound over all those questions. And in a sense, within your analysis, you can sort of imagine that the verifier has tested every single input. In the polynomial error dependence regime, if you're still thinking about a classical verifier, you can no longer do that. Somehow, intuitively, the verifier only has time to test polynomially many of these inputs, which is a vanishingly small fraction, and yet you still want some guarantee about all the inputs on average. So that's the sort of problem we are trying to tackle. And I don't have much time to go over the proof, but I think I might have time to give you maybe the most significant bit of how the proof works. And that's the division of the proof into two different theorems. So the first component of the proof starts with the test and the classical verifier and says that if these two players win the parallel repeated magic square game with probability 1 minus epsilon, then you can construct from their projectors that they're using, you can construct observables, and those observables must obey up to epsilon or square root epsilon, must obey the appropriate anti-commutation and commutation conditions. So in particular here in the observables, C and R represent the row and column indices. So R is an input for Alice. She's told a row. And C is an input for Bob. And K denotes the round. So K goes from 1 to n. There are n rounds in the parallel repeated magic square game. And so this statement is basically saying that if you're looking at any fixed round K, within that round, Alice's observables have to obey some anti-commutation relations. And if you're looking at two distinct rounds, then Alice's observables should always approximately commute. And that's one non-trivial step is you would like to intuitively say that the players are treating every round individually in a commuting way. But you can't say this a priori just from seeing the test. So that takes some work. That's the first part of the proof. The second part of the proof structure is the isometry component. So once you have observables that are appropriately commuting or anti-commuting, the next step is, well, there's a mapping from those observables to others, and for those other observables, there's an isometry which takes the W's, these new observables, and under this isometry, the W's act on the original shared state as Pauli measurements would act on the new shared state. So in other words, it's saying that this strategy must be close to the Pauli measurement ideal strategy that we want it to be close to under isometry. Okay. And it's this component of the proof that overlaps a lot with work of McCaig. So this is like self-testing results often have exactly this type of form. So these are two works. This is somewhat close to it, and this also overlaps to some extent with the Chao, Reichart, Sutherland, and Wittig. So the same group of authors as in Ray's presentation. Right. And I think I'm probably close to out of time or way over. So in conclusion, we prove a rigidity result for the parallel repeated magic square game. So it self-tests in EPR pairs with polynomial error dependence. And it certifies Pauli, like n times Pauli product measurements with polynomial error dependence. And it does all of this assuming you have a classical verifier and keeping the polynomial error dependence. And I'll list some quick open problems. So one open problem, or one problem that was open, is to reduce the error dependence, so to go from polynomial in n to constant. And that's actually done in a sum setting in this paper that Anand presented earlier. And another problem is to reduce the input size. So here there are exponentially many inputs, and you could want polynomially many inputs. And that's also done in some setting in this Chao, Reichart, Sutherland, and Wittig paper that came out in the fall. And then the big thing is to do both of these at the same time. So each of these papers does one and not the other. The big open problem is to do them both simultaneously. And then the rest of the open problems are the usual applications to these three areas where rigidity comes up a lot. Okay.
Thanks. So do we have questions for any one of the authors? One quick question. Yeah, so we are running a bit late, so I suggest that we move on to the next speaker. So let's thank the speakers again.